So okay, now we have to now we can like finally arrive at the expression of the Navier Stokes equation. So we started from this in the equations of motion derivation, and like we have already defined that sigma ij is minus p delta ij plus dij, and then we obtained the dij expression as 2 mu eij plus mu double dash delta ij ekk. So like if we finally substitute this into this and this into this, we can have the expression. So I will just substitute it. Using at all, you will do 1 by 2 delta ui by del xj plus delta uj by del xi. So we have like E of kk is simply is delta uk. Yeah, so now we can substitute the equation here. So let's just say what is delta of delta xj of p of delta ij. It's basically delta ij del p by del xj, and for I equal to j only this would be 1, otherwise it would be 0. So basically we can write this as del p by del xi. So we have del of del xj by p delta ij is simply del p by del xi. Now for dij, we have del of del xj of dij is 2 terms, del of del xj of 2 mu eij plus del of del xj mu double dash delta ij into ekk. So delta ij is a constant, mu double dash is related to 2 mu. So now we will see on the next page how to do that. So let me write del of del xj of 2 mu eij. It will basically 2 mu del of del xj of del ui by del xj plus del uj by del xi. So this would be simply it's half there, so mu times d2 ui by d2 xj plus d2 uj del of xi del of xj. Okay, so the second term was del of del xj of what was it, mu double dash delta ij mu double dash delta ij ekk. So first thing we have mu double dash as minus 2 by 3 times mu. Okay, so this expression is minus 2 by 3 times mu delta ij del of del xj of del of uk by del of xk. Okay, so here also similarly this thing we can replace by del of del xi, because only when j is equal to y this would be 1, otherwise the terms would be 0. So we can replace this as minus 2 by 3 times mu del of del 2 uk by del of xi del of xk. Okay, so we can replace now. Now we have obtained all the terms, so now we can substitute in the equation. We have rho of fi minus del p by del xi plus, let's see the equation, what was it, del p by del of del xj. So we have written this. Okay, so basically it is plus mu times del 2 ui by del 2 xj plus del 2 uj by del xi del xj minus 2 by 3 mu times del 2 uk by del xi del xk. Okay, so in this expression we can see that I is the free variable and j and k are the fixed variable. So here I can replace k with j also. So this would be del 2 uj by del xi del xj. So this would not cancel out, it would like subtract from these terms. So the final expression we would get is plus mu times del 2 ui by del 2 xj plus 2 by 3 1 by 3 mu del 2 uj by del xi del xj. Okay, so now we have obtained this expression. So one thing we need to emphasize upon in this derivation, we have assumed mu to be constant. Like if we do not assume mu to be the constant, then the generic expression of the Navier Stokes equation would be this only. Plus what was dij, 2 mu dij plus mu double dash delta ij ek. The generic expression of the Navier Stokes equation would be this only, or like in a better terms I can write it as rho dui by dt is rho fi minus del p by del xi plus del by del xj of 2 mu eij plus plus minus 2 by 3 mu del ij ek. This would be the generic expression of the Navier Stokes equation when we say that mu is not mu is not constant. But if mu is constant, we can arrive it to a much more beautiful equation in this form. Do minus del p by del xi plus rho f phi plus mu times del 2 ui by del 2 xj plus 1 by 3 del 2 uj del xi del xj. Okay, so this is the final expression of the Navier Stokes equation if we consider mu as constant. So now let us have a simplified version of the Navier Stokes equation when we consider the fluid to be incompressible. So if the fluid is incompressible, what we have is we have delta ui by del xi equal to 0. So here we see the delta uj by del xj terms is there. It's basically del of del xi by del uj by del xj. So this term would be 0. So we would have an expression of del xi plus rho fi plus mu del 2 ui by del 2 xj. And now by introducing the notation of the vector calculus, we can write it as minus gradient 0f, not mu, it's u. So this is the final simplified expression of the Navier Stokes equation for the incompressible case, assuming mu to be constant. This is the generic case where we do not assume even mu to be constant. This is the derivation when we assume compressibility, but mu is constant, and this is the most simplified version where we consider mu is constant as well as the incompressible nature of the fluid.